So hi, hopefully everybody had a great break. A question online was about exam 3 group, and it should be the same as exam 2. So there must be still an echo. There's still an echo. All right, is that better? Is there still an echo online? Is there still an echo online? All right, still an echo. Okay. All right, so. All right, so hopefully that took care of the echo on there. Online, the question was about that exam 3. And so I must have had an error. I thought I corrected it, so I apologize. If I can find the right. Of course not. So I might have linked the wrong link on the homepage, but they should be, these are the right ones. So you should be doing average value, RMS values, complex power, apparent power, average power, absorbed reactive power, and or power factor. So question related to those questions. Choose the load impedance ZL so that you get the maximum power transfer. So that was that power transfer. The ones we're going to we went through last time, but we're going to go over a little bit more today. And then next time is the next 2 problems, which are identifying what type of circuit you have as far as a filter. So is it, I didn't write them all. So low pass, high pass, band pass, or band reject. So those are the 4 types of filters we'll look at. So being able to identify what kind of a filter you have, and then being able to look and see the frequency that it operates to. So if it's a low pass, it's going to have up to a frequency. If it's high pass, it's going to start at some frequency and then pass it after that. Band pass will be a range, and band reject will be outside of the range. So identifying what those ranges are. So I'm not going to require you to know how to actually draw the graphs by hand, but to be able to interpret the graphs and determine from an equation what are those frequencies. So that's what you're going to need to know for the filters. And then we're going to go over Fourier analysis. So be able to express a periodic function in terms of the Fourier series using cosine, sine, the amplitude, phase, and the complex exponential representations. And then determine the spectrum of a periodic waveform and evaluate the Fourier transform of a non-periodic waveform. Being able to apply the Fourier transform technique to analyze circuits excited by a non-periodic waveform. So we're going to go over some of those examples today also. So that will be the content of what you'll need to do for the preparation for exam 3. This is also changed again, so you can either do it in your group, or if you don't want to work in a group, you can do it individually. So the purpose of it is to be able to prepare for the next exam. So whichever way is the best for you. All right, other questions? Oh, did I leave exam 2 on here somewhere? Okay. All right, so. All right, I uploaded these notes. The lecture 18, Fourier is the lecture notes. Anybody have access online that sees that they did get published? Okay, great. All right, so last time we did start talking about filters, looking at a circuit and saying, okay, how do I identify that this circuit is an actual, or what it is? So how you have to determine that is it's difficult to know from just looking at this, like, I don't know what this is. So how you're going to interpret this is by plotting what's called the Bode plots. So let me back up a second. So I recommend using MATLAB for this. That's going to probably be the easiest way to do it. Either MATLAB or an online calculator can plot these. For MATLAB, this would be the code that you would use. It's pretty simple. S is just defined as a transfer function. So TF stands for transfer function. And S just denotes that that's my variable of my transfer function. And then you just type out the transfer function, H2, and then you just do Bodhi. Bodhi magnitude. Oh my. Okay. Pencil's not working. My pencil not working. There. Okay. Don't know why this is, but Bodhi mag just means the magnitude Bodhi plot. So from the magnitude Bodhi plot is what you're going to interpret what this is. So I shortened the axis range, but you can just plot it like that. That's sufficient. And then here would be what that figure will plot look like. So you see that it does go down, does a big dip and goes up. So that is how you're going to see what it is. So looking at this, plot this, and then identify what it is. And then to determine what the frequency range is going to be. So that would go back to the transfer function, which again, the transfer function is output over input. And the easiest way is going to be to match this with, oh, lost the page. So this is going to be the easiest way to determine what those frequencies are going to be, is to match it with what form do I have from one of these types of magnitude Bodhi plots. I don't know what is going on with this. Okay. So from this, you have to put what is called the standard form for Bodhi plots. So the standard form is going to be where you get the S terms or the J omega terms, sorry, in depending on how you're solving it. If you're solving it in the Laplace domain, you can do it with S. If you're doing it in Fourier, it's going to be J omega. So for that, this is not. Ah, there we go. Okay, good. This is annoying. So the standard form is when you have 1 plus some number of S or some number 1 plus that number. So every term you want to get is in that 1 plus some number S or 1 plus some number J omega. Once you get it into that form, then you can look at that number by the J omega, like WC will be your cutoff frequencies. And so each of these, depending on what kind of a form you have. So sometimes you may not be able to get it into like 1 plus J omega or 1 plus a number J omega, and it's just going to be like a J omega term. Then that one won't have, that's going to be a polar 0 at the origin, and so it won't have a frequency omega C to it. All right, let's go through another example because this will make more sense this way. So take a minute. We want to solve this one using Fourier. So with Fourier, what you're going to do is just do it like we did with phasors back in 1240. So you would substitute it with J omega L for L, 1 over J omega C for C. And then the input is changed into the Fourier, which is what we'll go over next, but we'll change that into a Fourier either series or do a Fourier transform instead of the Laplace transform. Okay, so ignore the input for now because we're just going to take it V out over V input. So it's just going to be in terms of generically V out over V input. So go ahead and solve this one to get that equation of H omega.
All right, so hopefully you were able to get to this. If not, you can take a minute to figure out how to get here. The setup of the equation, I did node voltage. So this current was V naught minus VI over J omega L. This current was V naught minus 0 over 1 over J omega C. And this current was V naught over R. And then I separated out all of the V naught variables. So lumped those all together. And then took the VI over J omega L over to the other side. And then got a common denominator. So I made it J omega L R as the common denominator. And then that gave me R plus J squared omega squared LRC plus J omega L. And then when you have 1 over that term, you can flip it. So J omega LR comes to the top. And then it cancels out with the J omega L on the bottom of the other, VI over J omega L. And then to get it to standard form, I need to have a 1 in the front. So I divided out R from that term on the bottom. So when I bring out R, I have to divide all the other terms by R.
And when I do that, I end up with this end equation. So this is my V out over VI, or my transfer function. So I call this H of omega. Questions on how to get this? Did you guys get this? Questions? Yes.
I just have a question. Your reasoning for doing a j omega times the square root of LC squared.
You'll see that in a second.
Is what?
It's just because you'll see it in a second.
Is that like a pretty standard way of kind of representing that? The only reason I say is like I basically kept it as I just did j omega like that whole thing squared. So it feels a little more complicated to do it that way, but I guess I'm curious if is that like more standard way to see.
So did you just leave it in J squared omega squared LRC?
Squared together CL.
Yeah, I mean, they're the same terms. You'll see in a second why.
That's what I'm curious.
Yeah.
Okay. Thank you.
So from here, let's see, let's put in the numbers. So R was 100, L was 0.5 or 0.1. Let me just copy these down here. And C was 1 micro. So remember, where was the poles and zeros? Do you guys remember which one was which? I remember those. Opposite. Close though. So top is zeros and bottom is poles. So zeros are always on the top and poles are on the bottom. So from this form, you can see that it is going to be a quadratic, and because it's on the bottom, it will be a quadratic pole. And so looking at this form, we want to find omega C, which is going to be that frequency. And so looking at this term here, if you square it, then it's easier to see what that omega C is. So that's the only reason I did that. So from this, if you match that up, you can see J omega is in the top. So omega C will be 1 over the square root of LC. And that is directly just from that component there. And then you can figure out what the damping factor is. I don't even know. I want to say zeta. Anyway, yes?
Are we saying that we're the WC or we're saying the omega or is the omega?
Yeah, so omega C is our, sorry, yeah, that should be omega C. Omega C is what we want to find for this frequency range. And omega is going to be varied over a whole range of frequencies. Yes.
So in the one where we just created the transfer function, like written in red, that omega is actually omega C.
The top one is going to be omega. So, here, I'll back up. So J omega square root of LC squared is going to equal J omega over omega C squared. And so you see these two are the same. So they'll cancel out. Squared will cancel out. And then just solving this for omega C is 1 over square root of LC. So I'm just matching those terms, and then we can do the same thing to find the dampening. I think this is zeta. I'll have to look up again what that one is. That ends up being L omega C over 2R. I saw a hand. Their hand, question? Yes.
I was gonna ask, so does that mean that it can be like S or power?
Yeah.
Okay.
Yep, it can be to any power, correct?
We solve the. Or do you ever simplify it to practice revenue?
You can do it either way. It's just easier once, because you're gonna find omega C anyway. All right, so for our values of our omega C is gonna be 10 to the 5th radians per second. And the dampening coefficient is gonna be 0.05. All right, so now we wanna graph this and say what kind of a filter is this? So we're gonna move to MATLAB. Maybe. So I find it easier to do it in terms of S. So when you do this, all you need to do is change everything from J omega equals S when you type it in. So everywhere it's J omega, just plug in S. So this is going to be back here for a second. So S L over R plus S square root of LC squared. So that's going to be my equation, and then putting in the values, I'm going to have 1 over L was 0.1 milli over 100 plus S square root of 0.1 milli times 1 micro squared. So S equals TF of S. And then H equals, and you can do H1, H2, whatever H, or even a different variable. 1 divided by 1. Put this back in. Easier to do on a 1 over. Oh, my keyboard's not working. Okay, maybe not. The keyboard's not working. Not a good morning. S times. I can type here. Okay, so this is the Bode diagram of that. So what does this look like?
Low pass.
Low pass. Perfect. So there's our low pass. So we found that this frequency that it goes up to 10 to the 5th radians per second. You can see here has, you know, a pretty high Q that you don't want. So this would be a low pass. I will back and copy. Right, if you don't like to match it, see if you can, I don't know if this will work. Let's see, P equals. All right, I'm just seeing if this will work. I think it might. No, it didn't work. All right, never mind for that one. All right, questions on doing this?
Just leave it unsimplified, just to graph it to see that we can do it.
Yeah, you can, yeah, the reason to put it into the standard form is to match up to find what omega C is. But you can graph it and actually use the graph also to determine where that frequency is. So either way, those are just the information that you want to know is what does the graph look like? What kind of filter it is? What is my frequency ranges?
Why do we use a Bode plot, not just like a regular graph? What's the difference? Just like the
so a Bode plot is in, we haven't talked about this, but this is in dB. And so it has to do with our hearing. Alexander Graham Bell discovered what this was. He called it a decibel. He found that our hearing is logarithmic. And so if we were to graph what we hear, it wouldn't be a straight line. It's actually an exponential function. And so in order to make it look linear, he created this, which is a semi-log graph. The x-axis is a log and the y-axis is linear. And so the x-axis will be this log, and all the log is that for each decade, you can see here, it goes from 10 to 4 to 10 to 5. Each of these little ticks are logarithmic. And so it looks like this. So the first one would be 2 times 10 to the 4th, and then 3 times 10 to the 4th, 4 times 10 to the 4th, 5 times 10 to the 4th, all the way up to 10 times 10 to the 5th. And so it makes this a linear graph, and it's due to hearing. It's just what we hear. And so all of these graphs are in this semi-log form. And you will get into how to actually graph these by just looking at that equation in 2280. So we're not going to go into the details of how to graph that, but what you need to know and understand is what that frequency means. So omega C means a cutoff frequency, and then identifying what kind of a filter this is. And being able to get the transfer function. So analyzing the circuit for the transfer function. So those are the 3 things that you kind of need to know for filters. Is that clear what you guys are expected to know? Yes.
So then if we have in the like simple or the standard form, if there was like a band reject where that was like omega, that would be squared then, or something like that, where it would be plus or minus, or how would you?
Yeah. So this one was the band. Yeah, this was the band reject that we did last time. And so it ends up being still a squared. This is you can reduce it down to that squared form. And then from there you can get, there's going to be 2 roots. For a low pass, that squared gives you 2 roots, but they're the same. So that's why low pass and high pass will have that omega C be the same, because there's only one of them. But for the band reject and the band pass, you're going to get 2 when you solve the roots.
There are ways to like, how does like the dampening constant forever is called fit for the voting plot? Like, is that something where you can like get it from the plot, like you can for omega C, or?
So, no. I'll just say no. You use the equation. Once you find omega C, you use the equation. So you would find omega C from the plot, and then you would use the L omega C over 2R. Very hard to extrapolate it from the graph. But for the omega C, you can actually measure using a cursor on MATLAB and actually identify where that 3 dB point would be. So in this case, it ends up being at the, the peak because it's got such a high value there. All right, other questions? I think I saw another hand. So because this is a low pass, it's going to be, it will go, ideally, this should go from 0. This would be the ideal low pass. And so I don't know if that answered your question. So it will be where it changes by 3 dB away from the 0. So it either be 3 dB up or 3 dB down. So this one's going to be a little skewed because you have such a high peak there. So it's going to probably look like somewhere, let's see. There's 3. So this is probably 5. So it's going to be, I didn't draw that line very straight, but but it will actually extrapolate out pretty close to that 10 to the 5th. Yeah, my line where the Q was a little skewed. Yeah.
Everyone's kind of drawn the point as to what Q value is. Do you remember this?
So for a low pass, that Q value is that it gets a lot of ringing when it's high. And then when it was low was when you hardly had any ringing. So you want a really low Q for a low pass. But you can see in this one, we had a really big peak, so the Q was really high. So Q means something different for each type of filter. So first identify what kind of a filter it is before you say whether it's a high Q or not, or low Q. So what I would ask for Q, I'm not going to necessarily, well, probably not. We haven't done a lot of, yeah. I just probably just understanding what that Q means. So concept wise, what does Q mean? What does omega C mean? What does that bandwidth mean? And identifying which filters you have, and then is it a high or a low value? And that's more concept wise of just looking at the graph. All right, other questions? Okay. All right, so that's kind of the end of what you need to know for filters. Today there'll be an assessment. So it'll be similar to this, derive the transfer function, graph it, identify what filter it is, identify omega C's, and does it have a high or low Q? Okay. So Q has to do with what kind of a filter it is. So in this one, if you have a high Q for a band pass, that means that you have a really narrow region, which is good. So you want a high Q. For low pass, you want a low Q because you don't want that oscillation. And for a high pass, again, you want a low Q. And then for a band reject, you want a high Q also. It's just, yeah, it just shows the range, yeah. So you have, you have a range of bandwidth in there, but then you have the Q part of it too. So let's go back to this one. So is this a high Q or low Q from this one? This one has a high Q because the bandwidth was really, really wide. So Q and bandwidth are related. All right, any other questions? Yes.
I'm still a little confused on where you got the formula for omega naught. Such like, yeah, this is what your notes.
So this is in the book. Page, it's in chapter 9, page 516. What did I say? Page 516. All right, other questions? All right, so Melissa, I'll get to your question in a second because that will become more clear. All right, any questions on filters? So it's, oh yeah, it's page 516 of the book, but page 530 of the notes. Okay. All right, you found it now?
Yeah. I got it.
Okay. All right. All right, any other questions about filters before we move on? Yes. So just go to any of the links that, like you can even do your test your knowledge anywhere. And then just do the free and textbook initiative. And then click on the circuit analysis one and do the free download. All right, other questions? Yes, Taylor.
So the, that whole like move from omega to omega C. That kind of threw me off a little bit. And so I was just wondering, like, is that, I guess, is that detailed in the chapter? I hadn't seen that yet. I can't remember if we went over it last Monday or not.
No, I did not go over it last Monday.
Okay.
And the reason I didn't was because I just said to graph it.
Okay.
And then again, you can do it graphically. You can just use MATLAB and use your cursor and find where that omega C is
Okay.
on there. Or you can look at these equations and match them up. I'm not going to go into all of the derivations of it because you're going to do that in 2280.
Okay.
So that was why. So
I guess the thing that I'm kind of sitting here is when I look at like page 216, note like is it just always that JW to the time of the square root LC always equals JW over WC? So we just need to try to force it into that form.
Yep.
Okay.
Yep. So you just are forcing it into that form to get the 1 plus, you know,
Okay.
some number omega,
So then,
some number J omega.
and
and
then
then
for the
plus.
quadratic pool, I guess it's the same for the quadratic zero.
Yeah, it's just on the top or bottom is the only difference.
You kind of, it looks like you kind of shortcut it by just solving for the, like you knew they were equivalent. So like J, so all you're doing there is you're just trying to find what WC equals.
Mhm.
Like
Yep.
you're not actually solving for the roots, right?
Yep, just omega C itself.
So we know that once we put it into that form, you kind of said, hey, this equals this, then you can use that to solve for omega C.
Yep, it will always be that number that's multiplied by the J omega.
Okay. All right, thank you.
You can go through and actually solve the roots. They'll be the same.
Okay. But this is quicker.
Yep, this is just quicker. So this is where you're in 2280, you're going to learn how to actually look at this and then graph the whole graph.
Okay.
Otherwise, you can still use MATLAB to graph the whole thing.
Okay.
If you wanted to do it by hand, you have to pick one omega, solve that equation, take the whole magnitude of that complex number and plot that one point, and take a new omega and just do that for every single omega. And and then you have to do the phase portion of it. You have to take the phase of that complex number. And so it gets to be a little bit complicated. So I'm just giving you a shortcut.
Okay.
Because that's really the only information we really want from that is that omega C.
So the focus right now, sorry, I'm gonna be so silly, but the focus right now is understanding what omega C is, and then like what our Q value is.
Just whether it's high or low, not even the actual value, understanding like the bandwidth,
Yes.
what those concepts mean. And then omega C will be the only one you'll need to find an actual value for.
Okay, awesome.
Yep.
Are you gonna have the MATLAB code in your notes?
Yep, it's already in the previous one. And then, yeah, so if you download the notes from last time, I did include that from last time because I couldn't remember my syntax was wrong.
Yeah.
So I included that when I uploaded it. So it is in my last notes and then it will be here too. Uh-huh. All cases, yeah. It just depends on which way the graph's going.
Okay.
So if it's changing up, so it started, you can see where it's more flat. So when it goes up, it will be up by 3 dB. If you have squared, it might be 6 dB. So this actually should have been 6 dB because this was a squared, sorry. Or 3 dB. So if you have just a single S instead of an S squared term in that bottom, then it would only be 3 dB. This should have been 6 dB, sorry. I am a little bit off of it, but it will be closer here, which will look like it's more the 10 to the 5th. Yes.
So when you calculate that omega C value, you get 3.16 times 10 to the 5th. Here you have it as times 10 to the 5th. I'm just kind of confused there.
So when you measured it, it was what? At 6 dB?
It was, I just did the 1/square root of all C to calculate it,
Okay.
and I got that it was 3.16 times 10 to the 5th. We're looking at, I'm just confused, because like, we have that 3, I'm using the power to the 5th.
L was 0.1. Right, 1 times. Let me just, it should be the same, so I'm kind of trying to. I get 1 times 10 to the 5th, so I'm not sure. So 0.1 times 10 to the minus 3 times 1 times 10 to the minus 6 gives you 1 times 10 to the minus 10. You take the square root of that, it's 1 times 10 to the minus 5. And then 1 over that would be 1 times 10 to the 5th. You use, oh, okay, so L was 0.1 milli. No worries. I was like, it should be 10 to the 5th. I don't know. Okay, other questions? I saw another hand. Yes. Okay, go ahead.
How would you find omega not given this like transfer function? And it's not paramount. Because I just, if you wanted to like a key sign this, you have to change the bandwidth or the like not. I don't understand how to do that. So maybe not the resonance, right?
Yeah. Yeah, so omega naught and omega C are the same
In this case, or
in this case, yeah. So yes, that's why that looks familiar as 1/square root of LC is the omega naught for that RLC that we looked at before when they were in parallel and series forms.
So like if you're given a non, like a RLC circuit with like multiple elements, and not just like the simple RLC circuit, how would you find it?
It would be omega C.
Even if it had like two omega C's where it's like a bandwidth.
Oh, in that, no, for low pass or high pass, it will be an omega C. But for bandwidth, or that will only have bandwidth. You won't have an omega naught there because it's going to be a different form.
Then how do you find Q bandwidth? Or
Don't worry about it for now.
okay.
You can, but don't worry about it for now. There's a formula you can just use. You can relate omega naught to the bandwidth. But we're not going to be worrying about that for now.
You know what MATLAB toolbox you need to be running this?
It's the control toolbox.
Okay, thank you.
And it does come with, the control toolbox does come with the student edition. So just make sure that if you aren't seeing it, it's in your apps.
Yeah, I haven't installed.
Okay. All right, any other questions? Yes.
I know we went over this many times, but like say omega C is when the vote plot equals 6 decibels.
Mhm.
But also wouldn't it equal it twice? Because like it goes up and down.
So 6 dB from the flat region, I'll say. Oh, that was not good.
Wait, so it's just the first time it reaches, so it like goes up and then down.
Yeah, because this is a low pass.
Also for a high pass and from the right.
Yeah, so for the high pass, you're gonna find it when it changes. So it will come up and then go flat. So it's gonna be 3 dB from this. So in this case, or 6 dB because you have a squared in there. So this can also like dip down. So depending on which way it's changing, you'll measure it from that. The way this is drawn, you would measure this one at 6 dB above where that is.
Oh, look at the rest of so
It's not exactly at the peak. Don't worry about that one, but just if you're going to extrapolate it from the graph, that would be where you would measure it. It will be very close to it.
So omega naught, the resonant frequency, we should assume it to be the peak instead of defining by C for high pass or low pass.
Yeah. It will be slightly different, and there's a reason, but we're not going to get into why.
Okay.
But yeah, it could be slightly off depending on what your values are, because those, anyway, the poles and the zeros will affect that. All right, any other questions? Yes. Sorry, say that louder. So you just take whatever value is here and add or subtract like 6 dB. From whatever the flat value is for a low and a high pass filter. If it's, oh, you're asking why it's 6. So 6 is, it's a 3 dB for every polar 0 you have. And so we have an S squared on the bottom, so it's 6 dB. If we just had an S, so if we had a simple pole, so if we found that this was a low pass filter and our transfer function ended up just being S plus, or 2S plus 1, we would have only one single pole, and that would be then measured at 3 dB. So we would only go up 3 dB or down 3 dB. If this was cubed, it would be 9 dB. So it would go up by 9 or down by 9. So for each polar 0 you have in there, it goes by 3 dB. And 3 dB is equal to 1 over the square root of 2, which is that average RMS value. So that was where that comes from. It's because it's the average value. All right, any other questions about filters? Thoroughly exhausted them. Okay, so we're going to move on to the Fourier series. So what you need to do is understand Fourier series. So Fourier series is another technique, just like Laplace. We start off with the series portion because what it is it's a whole bunch of sinusoids that are added up to represent whatever signal we have. So if we have a square wave, it can actually be represented by a whole bunch of sums of sinusoids. So it has one big sinusoid, all these small sinusoids to give you so that it's almost exactly looking like the same graph. So the higher, it's called a harmonic for every sinusoid you add in there. So for every harmonic you have, the higher harmonic values you have, the more accurate it will have. So if I have 100 sinusoids in there, I'm going to have a much more accurate representation than just one, which would be just one sinusoid representing the square wave. You can represent it for any signal at all. If it's a sawtooth wave, you can again add up all of these sinusoids to represent that. Triangle wave, semicircle wave, all of these waves can be expressed in this form. It's a sine and cosine representation of the waveform, f of t. So A naught would be 1 over the time period t of 0 to t of ft dt. And A0 will be your, if you guys remember, this looks like an averaging, right? So this is your average value of the graph. AN would be all of the coefficients in front of the cosine terms, and BN is going to be all of the coefficients in front of the sine terms. So the nice thing and why we do this is because this helps us now get a representation of all of these coefficients that give you an idea of how much each frequency is contributing to the end waveform. And so not only now do we have, the magnitude, which is, an amplitude if we're talking about voltage, but we know how much contribution each portion of a frequency actually gives to that waveform. And that's really valuable information because then when we talk about filtering and we want to filter out a specific frequency, we can see how much effect that it has at each particular frequency range. All right, one nice thing is that if we have an even or odd function, Bn and An will go to 0. So if we have an even function, then Bn will go to 0. And if we have an odd function, do you guys remember what these were for even and odd functions? Oops. Anybody remember odd and even functions? It's been a while. No, okay. The first one was what again? Even things. Even and odd. Okay, graphically, what this looks like is that this would be an even function where you have the same value on each side. And odd, I'm not going to draw because it won't look as good. But odd is where it flips and then it rotates. So if you have those functions as far as your sinusoid, you can say that for an even function, all my Bn terms go to 0. So that makes it nice when you're doing these representations. For this original waveform, what kind of a waveform is this, even or odd? This is an even one. So this looks like even. So this shows you for each sinusoid that you add in here, you can see how it's getting to add to look more like a square wave. So the first one is with only one term, one sinusoid. The second one is when you add 2 sinusoids, 10 sinusoids, 100 sinusoids. So you can kind of see that they end up looking like a square wave. So with these, you can change this from the AN and the BN to just one cosine form and then make it into a complex form. So this would be changing it to look like a phasor. And this one is where we look at amplitude and phase. And on amplitude and phase, what we can do is show for each frequency a value of how much those contribute to each frequency. So this is called the amplitude spectrum and the phase spectrum. So for the amplitude spectrum, that shows you the contribution of each of these, and that is the graph of each of these for the magnitudes. The Fourier, so that's the Fourier series, and now we can do the Fourier transform from this. And if we're looking at the series, we can change that into an integral form. And so this is the integral form of that. It looks very similar to what we just did with Laplace, except for it's slightly different. And so again, we have transform pairs for the Fourier and a transform table. So next time we're going to go over an example and we'll solve these with Laplace and the Fourier, and you'll get to see kind of the difference between the two. All right, so today is the assessment for filters and then that quiz for the filter will be due by tomorrow. What? Yeah, quiz will be due by tomorrow night and the assessment will be due by tonight. All right, any questions online?